Hi, so I want to talk about Savitch's theorem, which is one of the great achievements in theoretical computer science and complexity theory. So the idea behind Savitch's theorem is we want to relate non-deterministic space running in a certain amount of space, so let's say f of n space, and we want to see, can we deterministically simulate this non-deterministic thing in some amount of space that's as close to f of n as possible, okay? So I want to deterministically simulate a non-deterministic thing with as little space as possible, okay? So I'm not gonna tell you what goes in here yet, which is what Savitch's theorem is. I want to arrive at what it should be, and then we can discuss the implications at the end. Okay, so let's just get something on the ground. What thing could we do to deterministically simulate a non-deterministic thing? Well, we've done this before. We've done this with non-deterministic time and deterministic time, which is doing the computation tree approach. So if we have some computation tree, what that looks like is the starting configuration at the top. And of course, there could be some number of non-deterministic choices that we can make, and each one of them has their own choices that they can make. So maybe this one has 4, maybe this one has 3, and each one of these has their own possibilities, etc. So we have a tree that looks like this. And what this is saying is that, well, what is the height of this tree? Well, it's going to be something along the lines of f of n, right? So how long could this tree possibly go on for? Well, let's see. What is the amount of space that we're allowed? We're allowed f of n space, or at least a constant times big O times f of n. So that means that the number of steps that I'm allowed to go down here could be exponential in big O of f of n, right? Because I could explore all possible configurations of size f of n or less. So in fact, the depth of this tree could be some exponential of big O of f of n. And the way that we usually write that, instead of it that way, we usually write it as 2 to the power big O of f of n. So if you needed like a bigger base right here, you just increase the constant up here, and that'll be enough. Okay, so we could just try all possible things that we could do at each one of these points, right? So we just try all possible things right here after one step, and then from each one of those we try all the possible things of 2 steps and just keep track of every single one of them. And if there's the configuration that has q accept, so let's say right there has q accept, which means that if there's some way to get from the top to the bottom, then that means that we will accept. We're just determining whether there's a q accept at some level here. Well, this brute force simulation is guaranteed to work, right? Because we just keep going down, 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 and eventually, if this thing is here, we'll eventually find it. So how much space does that use? Well, it depends on how big this branching factor is, right? So let's say that this branching factor, which is the maximum number of things we can do at each point, is d, let's say. So let's call d to be the maximum number of non-deterministic choices we can make at any point throughout the entire machine. Well, then the amount of space that's used in the whole thing here is going to be d times d times d times d times d all the way down this deep. So that means that I'm going to have 2 to the big O f of n, and then the whole thing to the power of d, which seems like a lot, but it turns out to be not horrible. It's 2 to the d times big O f of n. But the problem with this, of course, is that we're reusing space, right? So like here, if we have all these combinations, well, I have to keep them around when I'm exploring one node down. So let's say we're looking at that node and we're exploring one level deeper. These other ones are still here whether we like them or not. So if, like, say the Q accept is, like, say right there, then all of these other ones are taking up space and I don't need them to be there. For the time, we don't really know of a way to get around this, but for space, we can reuse space. We can't reuse time. So let's think about a different approach. So let's say that we find some middle point right here. So let's say right there, and maybe there's some path that eventually leads to the Q accept one. Then what we can do instead is think about a depth first approach versus a breadth first approach. Okay? So breadth first is what we were doing, looking at each level one at a time. But what if we did a depth first search example, for example? Well, let's say that I can figure out, okay, I can go from this top to the middle, and then I can go from the middle to the accept one. Then that means that I can get from the top to the Q accept state, right? So what we can do is do some kind of recursion where we go down one half of the recursion, which is seeing if we can go from this top to this middle. And once we're done with that, if we can get from here to here, then we throw away everything but the fact that we can reach there. So instead of, we don't need any of these configurations from the top to the middle once we figure out we can go from the top to the middle. Okay? So that's where the savings is. So instead of keeping all these configurations around, we throw them away once we know we can go from the top to the bottom. And then if we know that, then we ask, can I go from this middle one to the Q accept one? And if we can, that means I can go from the top to the middle and from the middle to the bottom. And so therefore, I can get from the top to the bottom, which means that we should accept that input at that point. And if we find that we can't get from here down to the pink node right here, that doesn't mean we should reject, but that means that this particular path doesn't work. Or if we find that we can go from the white to the pink, but we can't go from the pink to the green, it might be that these choices that we made here were not right. And so this pink node might not have been the right middle point right here. Maybe some other point might have been the right choice. And so if we reuse space and just throw away any hope of having a fast algorithm, just focus on a small amount of space, then we can actually show that we can get a very small amount of space compared to this humongous amount of space right here. Okay, so that's the idea behind Savitch's theorem. So how does Savitch's theorem actually work? So what we're going to do is we're going to define a function, which I'm going to call can yield. And it's going to have 3 parameters to it. So it's going to have parameters C1, C2, and T. And so what do these mean? All right, notability crash, so I'm going to try to continue from where we were. So what we're going to try to do is we're going to create a function called can yield, which is going to take 3 parameters, C1, C2, and T. So what are these parameters? So the C1 and C2, these are just configurations of the Turing machine. So the tape contents, the state, all that stuff. And the T parameter is the number of steps allowed. So what can yield is going to either return true or false. It's going to return true or false based on the idea that we had earlier. So what it means is return true if C1 can yield C2 in T transitions here. So actually you can define it in terms of at most T transitions. But T is the upper bound of the number of transitions that were allowed. Okay? So then we can actually define can yield in terms of itself as a recursive function. So how would that possibly work? Well, what is the base case here? So the base case is when T is 1. So if T is 1, that means I got to get from C1, which is just some configuration, to another one in at most 1 transitions. So it's either 0 or 1, obviously, right? You can't have a negative number of transitions. So then if T is 1, I should say if T is less than 1, then what we should figure out is if C1 is equal to C2, then that means we don't have to take any number of transitions at all. It's 0. So then if C1 equals C2, then we return true. Actually, I'm going to separate it out a little bit more. So if T equals 0, and they must be equal configurations at that point, and then otherwise we're going to return false. I know this is terrible code, but it's just to make it a little clearer. If they're exactly the same configuration, we return true, otherwise you return false. And then now what do we do if T is 1? Then that means that we need to apply a single transition from C1 and hopefully get C2. Note that there could be a whole bunch of possibilities here because we could have some non-deterministic choices that we can make. So what we need to do is to go through all the possibilities of a single transition. So what we should do is check if the Turing machine, or I guess the non-deterministic machine, because that's what we're trying to simulate here, can take C1 to C2 in one transition. Okay, and we return true if it is possible to apply a single transition to get from 1 to 2. Otherwise, we return false. Okay, so those are the base cases. And if we have, let's say, 2 steps, you may think, well, shouldn't we include 2? Well, if we have 2 or more steps, then that is composed of a pair of configurations with 1 or 0 transitions from one to the other, and another one from the middle guy to the last one. So if T is at least 2, then we can break this up into 2 recursive calls, which is nice. And that's exactly what we're going to do. So otherwise, what are we going to do? Well, what I'm going to do is we don't know. Actually, I should back up. So this pink node right here, I have no clue where it is. It could be right here. It could be over here. It could be way over here. We have no clue where it is. So let's just try all of them using f of n space. So if we use f of n space, because we know the Turing machine uses at most f of n times a constant amount of space, then that means that whatever configuration is right here, the one in the middle, I know it uses at most f of n space. So just try every single possible one with f of n space. So that's what we're going to do. So for all configurations, I'm going to call it C mid of at most big O of f of n space. Then what we're going to do is to figure out, can C1 get to this middle one in half that budget of transitions? Can we get to there with T over 2 transitions? So then actually what I'm going to do is return I'm going to write it really simply. So if we have the case of can yield from C1 up to C mid in T/2 transitions, and we have the case of can yield from the midpoint to the end, which is C2 in our case, that's what we called it. So in the same number of transitions, oops, I have it backwards. So from C mid up to C2 and also T/2 transitions, then clearly I can get from C1 to C2 in T transitions or less. And so therefore I should return true. Okay, and then if we try every possible midpoint and none of them work, I return false. So the way I'm going to notate that here is like this. So right here, I'm going to return false. Okay, and because we tried every possible midpoint and none of them worked. So either both of the can yields recursively failed or at least one of them failed. Okay. And so then that is the case of where we have some arbitrary configuration right here, and C2 is some arbitrary configuration right here, and T is some arbitrary amount of time. Well, how much, what should we do on the initial call? When we get the Turing machine, the non-deterministic machine, what should C1 be? What should C2 be? What should the time budget be? The number of steps needed? And that's actually really easy. So let's just say that I'm trying to simulate this machine. I'm going to call the deterministic machine M. So M right here is the simulator, the deterministic simulator, I should say. So it's going to get some input W, and I need to call can yield with some initial configuration and some accepting configuration. So here I'm going to say I'm going to return the result of can yield. I'm going to call the starting configuration C0. So that is going to be Q0 followed by W. And that's always the starting configuration no matter what you do. Then I'm going to have an accept configuration. And I'm going to talk more about that in a second. There are ways to get around that, by the way. And then the time budget is going to be, well, based on the tree that we had earlier, it could be exponential in f of n. In fact, it could be exponential in d times f of n. So let's set that to be the time budget, because it might be that much. So 2 to the d f of n. And I know we had a big O upstairs here. What we can do is we can increase either D or F of n so that we will exceed the amount, whatever the constant is in the machine. There's some constant for the machine. Just set these to be enough so where you get above that particular constant. So the only wrinkle in this, or actually there are two wrinkles. So C accept. There's always one starting configuration, but there could be many possible accepting configurations, right? Because the accept state could be anywhere in the result, right? So in the final configuration, the accept state could be pointing anywhere in the f of n cells. So what we should really do here is to try all possible C accepts of size at most big O f of n, or whatever the constant actually is. Okay, so we're gonna look at every single one of these can yields, and if any of them work, then we will return true. And since each one of these calls uses f of n space, and this uses some amount of space, we'll determine what that is in a sec, then that means that this is just only increasing the amount of space that are using by a constant factor. Because this is certainly going to use at least f of n space, and so this is just going to only add a constant to whatever that is. Okay, so then now, how do we actually figure out what the runtime of this thing is? So the other crucial thing, as I was going to allude to, is that what we need to do at these points right here, these two calls are the important ones, obviously. What we need to do is to erase the contents of whatever was used in those recursive calls before we go to the next one. So erase before the next call. Because we want to use as little space as needed, and we only need the one bit to say whether or not, say, like this one is true or not. In fact, we don't even need that. So if this first one returns false, don't even call the second one. Just go up here and then try again. If this one returns true, then you call this one, and that's what you will examine at that point. But you erase the tape, whatever was on the tape before, you erase it completely, and then before the next call. So that means that the amount of space that's needed in this whole thing is the amount of space at each of these recursive calls for one of these times the number of the depth of the recursion. So let's write that down. So the total space is going to be the amount at each call times the number of recursions, or not the number here, times the depth, I should say. So the depth of the recursion. Well, let's see. Well, what is the amount at each call? So the amount at each call, if we examine what we did here, we looked at every configuration of f of n size, right? So, and we never use more than f of n. It might be increase the constant, but it's some constant times f of n. So the amount at each call is going to be big O f of n. Well, here, what is the depth of the recursion? So that is the logarithm of the time budget that we started with. Why is it the logarithm? Because we're dividing by 2 on the time budget every single time. And we actually set it to be the power of 2 here, so we don't have to take floors and everything or ceilings. It just makes the math easier. But we're dividing by 2 every single time. So it's going to be the log base 2 of the initial time budget, which is this. So it's going to be big O of log base 2 of that 2 to the thing. So 2 to the d times, oops, I wrote it wrong, df of n. And if you simplify that, that's going to be d times f of n. And since now we need to multiply these together, so that implies that we're going to get big O of f of n squared times d space. Okay, so now what? Well, what is this n here? So n here is the size of the input. Okay, so n is the size of the input. Where does d come from? The d is an artifact of the machine. So the machine has a certain amount of non-determinism it can do. And since the machine doesn't change depending on the input, d is itself a constant compared to the input. If we wanted to talk about this in general, yeah, you would have the d right here. But since it's independent of the input string, therefore it's a constant, and we can reduce this to some other constant potentially times f squared of n space. So we went from exponential amount of space down to just the square amount of space, which is pretty awesome. So I'm actually not sure if there's even a better result known than this, whether you can actually get below 2 here. But the fact that you can simulate a non-deterministic thing with only a quadratic blow-up in the amount of space that is used is really awesome. So we can come back up here to Savitch's theorem, and we can finally fill this in to say that n space of f of n is a subset of deterministic f of n squared space, which is pretty dang cool. So if you have any questions about Savitch's theorem or about non-deterministic space or deterministic space, please put them into the comments down below. And you'll see me in the next video talking more about complexity theory.